Hello friends, welcome back to Webronaq. In this video, we're going to look at another way computers store signed numbers, and it's called excess notation. Now, in the previous video, we covered 2's complement in detail, how it flips bits, adds 1, and lets the CPU treat subtraction like addition. If you haven't watched that one yet, I'd recommend going through it first. I'll drop a card for it right here. But here's the thing. 2's complement isn't the only way to represent negative numbers in binary. There's another method, and it shows up in some really important places, like how floating point numbers store their exponent, the part of a float or double that handles the decimal scaling. Excess notation takes a completely different approach. Instead of flipping bits or using a sign bit, it just shifts the entire number line. And once you see how it works, it's actually one of the most intuitive systems out there. Let me break it down step by step. All right, here's the whole idea behind excess notation, and it's surprisingly simple. Look at the top number line on screen. That's how unsigned 4-bit binary normally works. With 4 bits, you can store values from 0 all the way up to 15. 16 total combinations, all positive. Now look at what excess notation does. It takes that exact same range, 0 through 15, and just slides it down. It subtracts a fixed number from every value. In this case, we're subtracting 8. So what used to be 0 now represents -8. What used to be 8 now represents +8. And what used to be 15 now represents +7. That fixed number we subtract, 8 in this example, is called the bias, or the excess value. And that's where the name comes from. Excess 8 means biased by 8. If we used a bias of 4, we'd call it excess 4. If the bias was 127, it'd be excess 127. The naming follows the bias directly. So the rule is simple. Take the binary pattern, read it as a normal unsigned number, then subtract the bias. Whatever's left is the actual signed value. For example, the binary 1100 is just 12 in unsigned. Subtract 8 and you get +4. So 1100 in excess 8 represents +4. That's it. No bit flipping, no sign bit, no carry tricks, just one subtraction. Now, you might be wondering, how do we pick the bias? Why 8 for 4-bit numbers and not some other value? Let's look at that next. So how do we pick the bias? There's a standard formula for it. The typical bias is 2 to the power of n-1, where n is the number of bits you're working with. That formula gives you a bias that splits the range almost evenly between negatives and positives. Let me show you what that means in practice. For 4-bit excess notation, n is 4. So the bias is 2 to the power of 3, which equals 8. That gives us a range from -8 to +7. That's the excess 8 system we just saw. For 8-bit, n is 8. So the bias becomes 2 to the power of 7, which is 128. The range works out to -128 to +127. Notice, that's the same range as 8-bit 2's complement. Both systems cover the exact same set of numbers, just with different binary patterns. But here's where it gets interesting. The bias doesn't have to follow that formula. It's a design choice. Look at the third card on screen. In the IEEE 754 floating point standard, the system your computer uses for float and double types, the exponent is stored using excess 127, not excess 128. The bias is 1 less than the formula suggests. That gives a slightly different range, optimized for how floating point math works internally. So the takeaway is this. Excess notation is flexible. The bias is just a number you agree on ahead of time, and it shifts the entire range to wherever you need it. Now, let's actually walk through converting a number step by step, both directions, encoding a decimal into excess notation and decoding excess notation back to decimal. All right, let's walk through this in both directions. Encoding first, then decoding. We'll stick with excess 8 to keep things simple. Look at the left side of the screen. We want to store the value -3. So how do we get its binary representation? Step 1, add the bias. The bias is 8, so -3 plus 8 gives us 5. Step 2, take that 5 and convert it to 4-bit binary. 5 in binary is 0101. And that's it. The number -3 is stored as 0101 in excess 8. Pretty straightforward, right? You're just shifting the value up by 8 so it becomes a positive number, and then writing that positive number in plain binary. Now let's reverse the process. Look at the right side. Suppose we read the bits 1110 from memory, and we want to figure out what signed value that represents. Step 1, read it as a regular unsigned binary number. 1110 is 14 in decimal. Step 2, subtract the bias. 14 minus 8 gives us plus 6. That's the actual signed value. So the whole system boils down to one rule. To encode, you add the bias. To decode, you subtract it. That's the entire mechanic. And here's something neat. Because we're just storing shifted positive numbers, comparing two excess notation values is incredibly easy for the hardware. The bigger the binary pattern, the bigger the actual signed value. Always. No special handling for signs, no edge cases. That property turns out to be really important, and it's the main reason excess notation is used in floating point exponents. Let's look at that next.
So why does excess notation exist at all when 2's complement already handles signed numbers? Here's the real answer. Look at the left side of the screen. In 2's complement, -3 is stored as 1101, and +2 is stored as 0010. Now, if you ask the hardware to just compare these two binary patterns as plain bit strings, 1101 looks bigger than 0010 because the leftmost bit is 1, which has the highest place value. But the actual signed value 1101 represents is smaller. It's negative. So the CPU can't just compare the raw bits. It has to first check the sign bit, then handle negatives differently from positives. That's extra logic in the circuit. Now look at the right side. In XS8, -3 is 0101, and +2 is 1010. And here, 1010 is genuinely bigger than 0101, both as a raw bit pattern and as the signed value it represents. The two orderings match perfectly. This is the real superpower of excess notation. The bigger the binary pattern, the bigger the actual number. Always. No exceptions, no sign bit handling, no special cases. That property is gold for hardware designers. It means the CPU can use the same circuit it uses to compare unsigned numbers, like array indices or memory addresses, to also compare signed values stored in excess notation. One comparator, every case. And this is exactly why the IEEE 754 floating point standard uses excess notation for the exponent of a float or double. When the FPU, that's the floating point unit inside your CPU, needs to compare two floating point numbers, the very first thing it does is compare their exponents. And because those exponents are stored in XS127, that comparison is just a plain bit-by-bit check. Fast, simple, no branching logic. It's a bit like sorting files in Windows Explorer by name. The system doesn't read each file name and interpret it. It just compares character codes directly. The ordering you see on screen comes from raw byte comparisons, because the encoding was designed so that bigger bytes mean later in the alphabet. Excess notation does the exact same thing for signed numbers. All right, let's bring it all together with a quick recap.
All right, let's wrap this up. 1. The core idea. Excess notation works by shifting the entire number line down by a fixed amount called the bias. No bit flipping, no sign bit, just a simple offset. 2. The bias. The standard formula is 2 to the power of n-1, where n is the number of bits. That gives you a balanced range with roughly equal positives and negatives. 3. The rule. To encode a signed value, you add the bias and store the result as plain unsigned binary. To decode, you read the unsigned value and subtract the bias. One operation in each direction. 4. The real win. In excess notation, a bigger binary pattern always means a bigger actual number. That makes signed comparisons effortless for the hardware, which is exactly why the IEEE 754 floating point standard uses XS127 for the exponent of every float and double your programs use. So now you know two completely different ways computers store negative numbers. 2's complement, which makes arithmetic clean, and excess notation, which makes comparison clean. Different tools for different jobs. If this video helped clear things up, hit that like button, share it with someone studying computer organization, and subscribe to Webronaq for more videos that break down the concepts your textbook glosses over. See you in the next one.